All right, exponential functions. So with exponential functions, they're in the form of f of x equals some number b raised to the x power. So your variable now is the exponent. And b and x are any real numbers, and b is always positive, and b is never equal to 1. So here's an example. Let's evaluate this f of x equals 27 raised to the x power for x equals 2/3. So that means that f of 2/3 is 27. Let me erase that dot there. 27 raised to the 2/3. That means take the cube root of 27, which is 3, and square it, and you get 9. X can be a negative number. So if we want to do g of negative 3/2, and g of x is 1/9 to the x power, that's going to be 1/9 to the negative 3/2, which means that's 9 to the positive 3/2, because if I have a negative exponent, I flip the base and it becomes positive. This means take the square root of 9 and cube it, and I get 27. All right, so how do we graph exponential functions? Well, they all have certain characteristics in common. The domain is going to be from negative infinity to infinity. The range is going to be greater than 0. And x-intercepts, usually we have none, but there may be that if it's translated down, you might have an x-intercept. Y-intercept is going to be 0, 1, and your horizontal asymptote is going to be the x-axis. Okay, that's if you have just a basic exponential function. Okay, so let's plot some points. So if x is 0, 3 to the 0 is 1. Okay, what if x was negative 1? Well, 3 to the negative 1 is 1/3. And as x gets more and more negative, this gets closer and closer to the x-axis on the left, but it never touches it. Okay, now what if x is 1? Well, 3 to the 1 is 3. What if x is 2? 3 squared is 9. So you see it goes up really fast. All right, so that's your basic graph of an exponential function. It passes through 1 comma b, whatever the base is, and negative 1 comma 1 over b. Now remember, b is always positive, but it could be a number between 0 and 1. And when that happens, then the graph will reflect around the x-axis. So 1 after the negative 1 is 2. 1 after the negative 2 is 4. 1 after the negative 3 is 8. 1 after the 0 is 1. 1 after the 1 is 1/2, and so on. And so now this graph decreases as we go from left to right. All right? Domain is still negative infinity to infinity. Our range is still greater than 0. X-intercepts, none. Y-intercept, 0, 1. And horizontal asymptote, y equals 0. Now, all of our familiar transformations apply to graphs of exponential functions. So notice that I'm adding 1 to x, which means we're going to go left 1 unit, and we're subtracting 2 from the entire function, so we're going to go down 2 units. Okay, so if you want, let's graph a quick 3 to the x. So 0, 1, 1, 3, 2, 9. Okay, so that's just y equals 3 to the x. Now I'm going to move everything to the left 1 unit. So this point's going to go over here, and this point's going to go over here, and this point here is going to go over here, and down 2. So now this drops down to here. This drops down to here. Actually, I dropped that down 3 units, didn't I? This drops down to here, and this drops down to here. And our horizontal asymptote will also drop down 2 units to y equals -2. And so now I just connect the dots that I just did, and there you go. One of the most common applications of exponential functions is compound interest. And this is our compound interest formula. A is the amount you have in your account after T years. P is the principal, the initial amount of money you put into the account. R is your interest rate, and it's got to be in decimal form. N is the number of times per year you're compounding your interest. You're calculating the interest. So if it's compounded quarterly, N would be 4. If it's compounded monthly, N would be 12. If it's compounded daily, N would be 365. And T is the number of years that you're leaving your money in the account. So here's an example. If $5,000, that's P, is invested in an account paying 3%, that's R, compounded monthly, there's N, how much will you have in the account after 7 years? So there's T. All right, let's put everything in. A equals 5,000, 1 plus 0.03, remember R has to be in decimal form, over 12, it's compounded monthly, raised to the 12 times 7. And I've got my calculator here, so I'm just going to punch everything in just the way it looks. 1 plus 0.03 divided by 12 raised to the 12 times 7. And we get $6,166.77. Now, if something's compounded continuously, that means it's compounded an infinite number of times per year. And what happens is it simplifies to this nice little formula. A equals P times the number E raised to the RT power. So let's do this with compounding continuously. So A will equal 5,000 times E to the 0.03 times 7. And fortunately, we have an E button on our calculator. It's right there over that LN button. So I'm going to punch it in exactly the way it looks. 5,000 second E to the 0.03 times 7. And I get $6,168.39. So I get a little bit better deal if it's compounded continuously.